Hello, good people. Welcome to the first video of the second topic in Unit 8. Unit 8, which is the applications of the definite integral. And the second topic here gives us a glimpse into something we've already talked about, which is how to connect the parts of motion that we deal with, such as position, velocity, acceleration. So just as a quick recap, remember that in the fall semester, we discussed that position tells us the location of the particle, tells us where the particle is, right? Velocity tells us how fast and what direction the particle is going. And then acceleration tells us how fast the velocity is changing. And I call it the push, right? When I have positive acceleration, I'm giving a push to the moving particle in the right-sided direction. Or if I have a negative acceleration, I'm giving a push to the velocity of a moving particle, but to the left. Anyway, but this is what we had talked about before. And we said that in order to get from one to the other, we had to take the derivative. Take the derivative. So to get from position to velocity, I had to take the derivative. So velocity is position prime. And then to get to acceleration, well, that would be velocity prime, which would then also lead us to be the second derivative of position. Now, normally I don't use P for position. We use like S, or we use X if it's moving in a sideways direction. But that would be position is S of t. Then I would just take the derivative and keep on taking the derivative. But now that we're in the world of integrals, where we can actually go backwards, then we can say with certainty that if I start with acceleration to go back, then I need to do an antiderivative or an integral. And if I want to go back, I need to do an antiderivative or an integral. And so now that we know how to go quote unquote backwards, we're going to practice that idea with these three concepts that we studied in the fall semester. Okay, so that's how we're going to start. And here's going to be our first situation. We know there's a particle, and it is moving along the x-axis with an acceleration of a sub t equals 12t minus 4. We know that the particle's velocity is 18 centimeters per second at time 2, and we know that its initial position of the particle is 8 centimeters. The question is, what's the function x of t that represents the position of the particle? Okay, so let's think about what we want. This is what we want. And then let's think about what they give us. So we're starting here, and we want to end up here. So that means in the course of our work, we will have to do two integrals or antiderivatives, right? We got to go backwards to get the velocity first, and then we got to go backwards again to get the position. So all we're doing is the reverse of what we did before. So let's start with what we know. We know that the acceleration a of t is 12t minus 4. I guess I don't need to write that, but I'm writing that because I'm going to find the antiderivative of this, which means I'm finding the antiderivative of 12t minus 4 in order to get the velocity. So to go backward to get the velocity, I'm going to take the antiderivative. So the antiderivative of this would be 12t squared over 2, which is going to reduce down to 6t squared, minus 4t. However, I have to put a plus c. So now I know that the velocity equation is 6t squared minus 4t plus c. But I need to know what that constant is. And luckily, they told me a piece of information that I can use. They said the velocity is 18 centimeters per second when time is equal to 2. So therefore, I know the velocity is 18 when my time is 2. And in so doing, I can figure out and evaluate the C constant for this particular situation. So since they gave me what is called an initial condition, they tell me a piece of information at the beginning, I can solve for the constants and get the exact velocity equation. Otherwise, I just have a velocity equation that includes a plus constant, but I don't know what that constant is. So the orange piece of information, the orange circled piece of information, is going to help me get the exact answer. So I still have 18. This is 24 minus 8 plus C. I think that's 24. So this is 16. And if I subtract that over, that means C equals 2. Great. So I can come over here and I can say with certainty that my velocity is, or I guess I can do it here. My bad. I can say that this is a 2. So my velocity formula, my velocity equation is 6t squared minus 4t plus 2. But I'm not done because that's not what I want. I want the position function. So that means I have to take another antiderivative. I have to integrate this once again. So this will be the integral of my velocity, which is this. And I got to find the antiderivative. Okay, the antiderivative of this would be 6t to the third over 3 minus the antiderivative of this would be 4t squared over 2 plus the antiderivative plus c. So here I have my position function. But again, it's a generic position function because I don't know what the c value is. However, I do know another piece of information that they so very nicely gave me. They told me the initial position of the particle is 8 centimeters. So I know the position is 8 when, well, when is this? The initial position. Well, if it's the initial position, that means time is equal to 0. By the way, I'm reducing this and saying this is 2 t to the third, but my t value is 0 because that was the initial position at time 0. 4 divided by 2, 0 squared plus 2 times 0 plus c. Oh, well, this is just going to tell me that that the c value is 8. Therefore, I now have my position function. 2t to the third minus 2t squared plus 2t plus 8. If this is the position function, the initial position of the function is 8. Check. If I take the derivative at 2 will be 18. And if I take another derivative, the acceleration formula would be 12t. And it works out. So the big idea is we're using the same concepts from motion from the first semester with derivatives. We're just going backwards and figuring out our formulas that way. And if at any time we have a plus c when we take an antiderivative, look for extra pieces of information that can help us solve for that constant c. We'll come back in the next video and we'll get our calculator to do some more work for us.